Welcome to Tech for Novice, a technology channel for people with little or no technical background. If a laptop or desktop PC is slow, then two of the main possibilities are low RAM capacity and slow boot disk drive. Increasing RAM capacity and boot drive speed could significantly boost PC performance. Logic behind these two bottlenecks is explained in the video. Simple PC hardware upgrades you should consider to enhance performance, whose link is given in the description below. System can access more data quickly with more RAM by reducing the need to transfer data to virtual memory, which is part of slower storage devices, resulting in faster operation. Virtual memory extends the capacity of physical RAM to allow a system to run larger and more applications by temporarily storing less used data on it. Faster boot dive improves performance significantly as programs will load faster and virtual memory on it will be more efficient. Avoiding virtual memory completely is practically impossible as installed RAM capacity is far below required for all scenario due to high cost and motherboard specifications limit. Installing RAM and disk drive is relatively simple, but some homework is required to select suitable RAM and disk drive for addition or replacement. Compatibility, speed, required capacity, and available space for installation are the main specifications we need to consider. Solid-state drive or SSD is the common choice for disk drive upgrade due to high speed and robustness in comparison to traditional spinning hard disks. Double data rate random access memory or DDR-RAM is the most common type of memory used in computers. Understanding SSD and DDR-RAM is the basic requirement for selecting SSD and RAM suitable for a PC. Solid-state drive is a data storage device built with semiconductor chips like USB flash drive. Data is stored as electrical charges while traditional hard drives use spinning magnetic platter to store data. SSDs are more compact, significantly faster, more durable, and less susceptible to mechanical failure than HDDs due to no moving parts. Since HDDs use mechanical parts to read and write data, there is a lot of latency, mainly due to speed at which the platters spin and time for read and write head to physically seek out the correct area of the platters where the data is going to be read from or written to. SSD form factors include 2.5-inch, M.2, mSATA, AHCI or add-in cards, and U.2. SATA SSD, which uses AHCI protocol, has speed up to 600 megabytes per second. 2.5-inch SSD fits in 2.5 laptop HDD space and uses the same data and power connectors. SATA SSD is also available in more compact form factors, such as M.2, which replaces mSATA. Unlike other SATA SSDs, 2.5-inch SATA SSD needs two cables, one for data and second one for power, often combined in one connector. NVMe or Non-Volatile Memory Express Protocol is a high-performance storage protocol designed for SSDs that connects directly to the computer's PCI Express or PCIe bus. NVMe SSD is primarily available in the M.2 form factor with PCIe interface. NVMe PCIe Gen 3 SSD speed is up to 3,500 megabytes per second. Gen 4 SSD speed is up to 7,000 megabytes per second and Gen 5 speed is up to 14,000 megabytes per second. M.2 is a form factor that defines a physical size and physical connection type. It can use different data transfer protocols including SATA and NVMe. M.2 uses code in WWLLHHKK format for width, length, thickness, and key type. The first two digits are width in millimeter, second two or three digits are length in millimeter, third part indicates components on single side or both sides and components height in millimeter. Last part indicates key type. Take 2242 D2BM as an example. It is 22 millimeters wide, 42 millimeters long, components on both sides with 1.35 millimeters height each, and with B and M keys. M.2 cards used in PC usually have A plus E, B, M, and B plus M keys. M.2 SSDs have a width of 22 millimeters and the length can be 30, 42, 60, 80, and 110 millimeters, with the most common length being 80 millimeters. M.2 cards connectors look similar, but they are keyed in a slightly different way to prevent inserting them in an incompatible motherboard socket. M.2 PCIe NVMe SSDs are M-keyed and SATA SSDs are B+ M-keyed in general with few exceptions. B+ M-keyed slots are physically compatible with B, M and B+ M-keyed SSDs, but may not support both NVMe and SATA protocols. Check motherboard specifications if both protocols are supported and BIOS configuration required for the installed SSD protocol. B+ M key offers broader compatibility with devices accepting either key type but are limited to PCIe 2 lanes or SATA speeds, thus offering moderate bandwidth. The standard width and length for M.2 Wi-Fi and Bluetooth cards are 22mm and 30mm, with some exceptions such as 16mm width. They have A, E or A+E keys. PCIe or Peripheral Component Interconnect Express Bus is an interface standard for connecting high-speed components. Desktop PC motherboards have a number of PCIe expansion slots to add graphics cards, Wi-Fi cards, capture cards, adapter cards, etc. whose number and size varies with motherboard. PCIe slots come with different number of data routes called lanes, denoted as X followed by number of lanes. PCIe X1 slot has 1 lane, X2 slot has 2 lanes, X4 slot has 4 lanes, and so on. Transfer speed of a PCIe slot is transfer speed of single lane times number of lanes. PCIe versions are denoted as PCIe followed by generation numbers such as PCIe Gen 3 or simply PCIe 3. Every successive PCIe version doubles its lane transfer speed. Gen 5, 3.938 GB per second, Gen 4, 1.969 GB per second, Gen 3, 0.985 GB per second. Each generation of the PCIe interface maintains backward compatibility, but when two generations are mixed it operates at the speed of the slower generation. PCIe slot is also available in compact form factors such as M.2, designed for ultralight, thin and power-efficient mobile platforms, such as tablets, smartphones. Maximum number of lanes supported by M.2 PCIe slot is 4. While considering to replace or add an SSD, form factor, space available, protocol version, allowed lengths and key types should be checked. Transfer speed should be up to maximum speed supported by the motherboard as no speed gain with higher speed. Higher speed could be considered if price is lower or intended for later use with faster PC. At least 250 GB is suggested for system disk and some data, more capacity to store large volume of data. For 2.5-inch SSDs, main consideration is capacity as no difference in physical size and little difference in speed. If the motherboard has no M.2 sockets, then 2.5-inch SSD is the only option for laptops, while desktop PC may opt for M.2 PCIe expansion slot adapter to install M.2 SSD. If M.2 slot is available, then SSD should be either SATA or NVMe version. Existing SSD version should be the choice for replacing existing M.2 SSD. Dual mode M.2 slot can opt for either SATA or NVMe irrespective of existing SSD type, but may need to set up BIOS. If M.2 slot is empty, then selecting compatible SSD could be a little bit more complicated. You may check motherboard specifications to find out supported SSD versions. The slot's physical characteristics, such as key type, can also provide clues about compatibility. If the slot has B or B+M keys, then it is most likely SATA version, and if it has only M key, then it is most likely NVMe version. PCIe interface has evolved several generations which are backward compatible. If SSD and M.2 slot generations do not match, then transfer speed is limited to lower of SSD and M.2 socket speeds. Width of M.2 SSDs is 22mm, but length could vary. Some motherboards allow more than one length with screw position prepared for each allowed length. Some motherboard can fit longer SSD but may lack screw hole for shorter SSD to secure it. Flexibility of adding a SATA SSD drive to a desktop computer is unprecedented, provided a free SATA port is available. It can be placed anywhere, stick on case wall, place on case bottom, or just hang with the power and data cables at any space available within the box. No need to worry about cables lengths as they are available any length you need. Of course, you may use 2.5-inch drive bracket to make the components tidy inside the box. If all SATA power connectors are already occupied, then you may use splitter cable for additional SATA SSD. Even if SATA power supply cable is not available within the box, MOLX to SATA converter can be used. M.2 SSD can be installed on a desktop PC even without M.2 socket on the motherboard by adding M.2 PCIe expansion slot adapter. SATA SSD is cheaper option with satisfactory performance for PC without M.2 slots. Now let us see how to select RAM module for replacement or addition to increase capacity. For RAM module, we need to check form factor, supported generation, clock speed, CAS latency, ECC, available number of RAM slots, and estimated required capacity. RAM or random access memory is very fast volatile memory used for temporary data storage for quick access by CPU. More RAM means more data can be read almost instantly, unlike data on HDD and SSD. DDR SDRAM, double data rate synchronous dynamic random access memory, is the most common type of memory used in computers. DDR SDRAM transfers data twice on each clock cycle to double data transfer rate, which is the reason for using the term DDR. DDR, DDR2, DDR3, DDR4, and DDR5 are different generations of DDR SDRAM, which are not compatible with each other. Each generation has several clock rates. Higher clock rate means higher speed. DDR SDRAM has two module naming conventions. First format is DDRX followed by clock speed in megahertz multiplied by 2, where X is the generation. It describes technology, generation, and number of data transfer each second. For an example, DDR 43200 is DDR Gen 4 RAM with data transfer rate 3,200 million transfers per second. Second format is PCX followed by data transfer rate in megabyte per second, where X is the generation. It also describes generation of DDR memory, with theoretical maximum data transfer rate or bandwidth or volume of data transfer each second. For an example, PC4-25600 is Gen 4 RAM with 25,600 megabytes per second data transfer rate. DDR4 3200 and PC4-25600 are both Gen 4 with same clock speed and therefore same memory type. We can derive their relation with the calculation. With 1,600 MHz clock rate, bus transfer rate is 3,200 megatransfer per second, as there are two transfers each clock cycle. 64-bit or 8-byte of data is transferred each time. Therefore, bandwidth equals 3,200 times 8 megabytes per second, which equals to 25,600 megabytes per second. RAM modules are available in two common form factors: DIMM or dual inline memory module for desktops and servers, and SO-DIMM or small outline DIMM for laptops and other compact devices. DIMMs are 133.35 mm long and have 184 or more pins depending on generation. DDR5 and DDR4 have 288 pins. DDR2 and DDR3 have 240 pins and DDR1 has 184 pins. SO-DIMM are 67.6 mm long and have 200 or more pins depending on generation. DDR5 has 262 pins. DDR4 has 260 pins. DDR3 has 204 pins, and DDR2 and DDR1 have 200 pins. Key notch on a DDR memory module is at unique location for each generation. It makes sure that only compatible RAM modules can be installed on RAM sockets and helps to align tiny metal pins correctly. ECC or error correcting code drum automatically detects and corrects errors in data storage, preventing data corruption and system crashes. ECC RAM is used in mission-critical servers, workstations, and systems handling large amounts of data where reliability and uptime are paramount. It is too expensive for consumer-level computers. Consumer-level computers use non-ECC or non-parity RAM, and therefore no need to consider EEC RAM for upgrade. CAS or column address strobe latency is the delay in clock cycles between the read command and when data is available from the RAM. It's a crucial measure of RAM responsiveness. with a lower CAS latency value generally indicating faster performance. However, true latency depends on both CAS latency and clock speed, as faster speeds can compensate for higher CAS latency values. CAS latency is expressed as CL or CAS followed by number of delay clock cycles. DDR4 3600 RAM with CL15 has a true latency of 8.33 nanoseconds, which is time required for 15 clock cycles. With CL19, true latency is 10.56 nanoseconds. True latency can be calculated by multiplying CAS latency value and time for one clock cycle. Clock rate of DDR4 3600 RAM is 1800 MHz. Therefore, one clock cycle equals 1 over 1800 microsecond. True latency for CL15 equals 15 times 1 over 1800. Microsecond equals 0.00833 microsecond equals 8.33 nanoseconds. Newer generation RAM generally have better storage density and power efficiency. They also have higher CAS latency, but overall performance is better due to faster clock speeds. We can select suitable RAM module with the technical information we have so far. For form factor, it is obvious that DIMM is for desktops and SODIMM is for laptops. As only one generation of RAM is supported by a motherboard, we don't have any choice. It must be the same generation as existing RAM. Check existing RAM and PC specifications if not sure about the generation. Clock speed should be same as system bus speed or current RAM speed. Higher RAM speed could work, but its speed will be dragged down to lowest of RAM modules and system bus speeds. In other words, higher RAM speed will not provide any benefits if system doesn't support it or when used with lower speed RAM module. Same CAS latency is recommended for all RAM modules, as all modules will operate at the slowest CAS latency present. Therefore, higher CAS latency of a single module can reduce overall system performance. Non-ECC RAM for commercial PCs, as costly ECC RAM is not supported. After deciding the correct RAM type, we need to decide on number of modules. It depends on number of available memory slots, capacity of each module, overall capacity supported by the system, and capacity we need. It is noteworthy that RAM modules should be installed in pairs or groups of 3 or 4 on many motherboards to enable multi-channel memory architecture, such as dual-channel mode. Multi-channel memory architecture allows the memory controller to use multiple data channels simultaneously, effectively increasing memory bandwidth and improving overall system performance by reducing wait times for data retrieval. To enable multi-channel operation, memory modules must be installed in compatible slots and matched in terms of size and configuration, often sold as matched kits. No magic number for how much RAM is sufficient, as it mainly depends on how the PC is used. If the system doesn't use all of available RAM on a regular basis, then adding more won't have noticeable impact. Please watch the video whose link is given in the description for more details. For the best and most stable performance, it's recommended to use RAM modules with identical speeds, timings, and voltages. SSD stores information data by trapping electrical charges which remain for years, even when power is off, making the storage non-volatile. Data is read from or written to an entire page of strings at a time, using specialized controllers and selectors to manage the charge levels. All trapped electrons are forcibly removed from the cells during data erase. SSDs mainly use NAND flash storage with memory cell as base unit to write data. Each memory cell stores a certain number of bits, and each bit stores 1 or 0. Each memory cell of a single-level cell or SLC SSD stores 1 bit, multi-level cell or MLC SSD stores 2 bits, triple-layer cell or TLC SSD stores 3 bits, and quad-level cell or QLC SSD stores 4 bits. SLC cell has 2 distinct charge levels to store 1 bit of data, 1 for 0 and 1 for 1. MLC cell has 4 distinct charge levels to store 2 bits of data, 00, 01, 10, or 11. Similarly, TLC cell has 8 distinct charge levels to store 3 bits of data, and QLC cell has 16 distinct charge levels to store 4 bits of data. Each charge level corresponds to a specific voltage level. When writing data to a cell, A precise amount of charge is injected to create one of the possible voltage levels. SSDs with more bits per cell pack more capacity in the same package size than SSDs with fewer bits per cell, but sacrifice relative speed, reliability, and durability. SSDs with more bits per cell are less durable due to wear and tear from a greater number of read and write operations per cell, and less reliable and relatively slower due to complexity involved in storing and reading more charge levels. Advantage of SSDs with multiple bits per cell is compactness and lower price. TLC SSDs are most common due to better price for overall performance. Budget SSDs where cost and capacity are prioritized over endurance and speed are QLC. SSD durability is expressed as TBW or terabytes written, which is estimated number of terabytes that can be written to an SSD drive before it fails. SSDs have limited writes because the process of storing data, which involves trapping electrons in an oxide layer, gradually wears down this insulating material. With each write cycle, electrons are forced through the insulator, causing it to deteriorate and develop small holes over time. Once the gate oxide fails, the flash memory cell can no longer reliably store data, which limits the overall write endurance of the SSD. SSDs do not need defragmentation like traditional spinning hard disk. Attempting to defragment an SSD unnecessarily shortens its lifespan by consuming limited write cycles, while the trim command performs necessary optimization. SSD cache is a small storage section to store data temporarily before writing to the drive. Cache section is usually faster and more durable than rest of the SSD memory cells as they are typically comprised of SLC or MLC NAND or partitioned to operate in SLC or MLC mode. Some SSDs have DRAM or dynamic RAM for cache, which is not only faster but also more durable. Caches are critical for boosting SSD performance, especially for boot drives and random write. Thank you so much for watching. If you like this video, please comment, share, thumbs up, subscribe, and press the bell icon.